All right, it's 12:30. We'll go ahead and we'll get started here. All right, just have the PowerPoint up here. 3D. There we go. All right. Okay. I will also get this chat box going here as well, just in case anybody's having some audio issues. Yeah, I don't know what was going on this morning, but Zoom was down, well, pretty much all down the East Coast, and it took them a few hours to get it fixed. It's been down since about 8 a.m., and I think it got fixed around. Hello, Victoria. I see that you did get here. That's good. And I think what happened is, I don't know what happened, but it took them about 4 hours to get everything fixed. But it looks like it's pretty much fixed now for a lot of people, which is good. I'm sure people will trickle in as things get fixed. Okay. So what we're going to do is I'm going to focus first of all on this hybrid orbital stuff, and then we'll get on to, I'll go back and I'll show you the test questions or test question that pertains to what we talked about on Wednesday. But we're going to do some other stuff now that's part of that same question. So once I get that done, then we can go back and take a look at that at the end. Now, I'm going to kind of gloss over this. I'm really expecting that people will watch the video to get more information about what I'm doing here. But I'm just going to go through the basics of this and make sure I have enough time to go over the test questions. Okay. Oh, thanks, Rebecca. I actually wasn't interested in roofing. I was more interested in vinyl plank flooring.
That's hilarious. Well, you're on the wrong site.
So home improvement, it was, anyway.
Yeah.
Anyway, thank you for the tip. I'll make sure that gets recorded. All right. So we're going through, we got S orbitals, P orbitals, and this is back from, I don't know, General Chem 1, Intro Chem. You would have looked at orbitals. What are orbitals? Orbitals are spaces or volumes where we can expect to find certain energy levels of electrons. If you'll remember, we have these, oh no. All right, let's get this brushes underway here. Come on. There we are. All right. Okay. So if you remember something like carbon, for example, it's 1s2, 2s2, 2p2. Right, and the way we get that is we look at the periodic table. I'll go back to the periodic table here. I have. And you got 1s2, don't worry about the hydrogen helium, it's just mentioned twice. 1s2, then 2s2 for these guys here, and then 2p2 over here. So this is the p block over here. So S block, P block, D block, F block down here, which isn't shown, but we're not really interested in that anyway. So if this is something that you need to go back and look at, you should. We've kind of gone through this before, or you should have seen it before. Okay, so that's going to form the basics of what we're doing here. And these are what these orbitals look like. So the S is kind of like a sphere shape, and the P is kind of like a dumbbell shape, but one along each of the coordinate axes X, Y, and Z. It's only 2 electrons per orbital. So you've got 2 in the S block, there they are there, and you've got 6 in the P block for the 3 different P orbitals. Okay, so if we were to look at carbon, you can see that I've got it over here actually. If you drew out what the orbital diagram looks like, you'll have the 1s down here, then you'll have the 2s, and then you'll have the 2p here. The 2p is 3 orbitals that have the same energy. They're called degenerate because they have the same energy. And we obey Hund's rule when we fill these. So we go from the bottom to the top, that's the Aufbau principle, and then when we get to these degenerate or equal energy orbitals, we have to put in one at a time. Right? So you might remember having to do something like that. Now, if you look at carbon, you can see it has two unpaired electrons here, and you could be forgiven for thinking, well, if we see two unpaired electrons, that probably means it can only bond twice. And that would be true if carbon maintained this kind of energy level electron configuration, but it doesn't. It doesn't do that. What it will do is it will do something called hybridization. And hybridization is exactly what it sounds like. It is the joining or combining of different orbitals to form other kinds of orbitals. So what we know is that carbon will actually be capable of bonding 4 times. And if you've got a compound that has 4 bonds to it, then you're going to need to have 4 equal energy level electrons. And we can do that by taking these s and p orbitals and hybridizing them, combining them together to form these new hybrid orbitals. So I've got an example here. Let's say we've got our s and p orbitals here, and I've got blue for the s and I've got yellow for the p's. And what I want to do is combine the s's and p's together and form these new hybrid orbitals, which are what I'm calling Sp3 hybrids. Now, where's that name come from? Well, it's from the combination of 1s and 3 p orbitals, 3 separate p orbitals like this. So we get 1 sp3. So think of it this way. We've got 1 blue and 3 yellows. If we combine them all together, what we'll get is something green. Yellow plus blue equals green. So then what we can do is take those electrons and combine them each here. Now, another way of looking at this, let's make this vodka and orange juice. Okay, vodka and orange juice. What's this over here? Anybody can tell me?
Screwdriver.
Screwdriver. Thank you. Thank you for the chorus. Screwdriver. That's exactly right. And a screwdriver is, in this case, 1 part vodka, 3 parts orange juice in this instance. So we get our screwdriver over here, and then we pour them back into the initial glasses here that we had, these same glasses over here. And we've got each of these is a screwdriver, a combination of vodka and orange juice, just like these are a combination of s and p orbitals. Now, I showed you over here what the s and p orbitals look like on their own. So let's look at what an sp3 hybrid orbital looks like. Well, that's what it looks like. Now, an sp3 hybrid, as you might expect, looks more like a p orbital than it does an s orbital. Let's look at what an s orbital looks like. It's kind of spherical, right? Look at the p orbital. See how they're dumbbell shaped? So the sp3 hybrid kind of looks like an elongated dumbbell like this. So it's got aspects of the s orbital, but more aspects of the p orbital. Does anybody have any questions so far? All right, so what we're looking at here are, I'm going to give you 3 examples. So that's got 4 bonds to it, and you can see that, or 4, actually, let me be more specific about that. 4 objects on C, okay. So 4 objects on C, which means we need 4 hybrids, which means each of these is sp3 hybridized. This situation has 3 objects. Now notice that I needed, to get 4 objects here, I needed 4 hybrids, which means I need to use 4 orbitals to get those hybrids. So I've got 3 objects here, and that's going to be sp2. So I need 3 sp2 hybrids to do that. And this last one has 2 objects on C. And I would call that an sp hybrid. So that's just a combination of one s and one p orbital. So if you look closely at these pictures I have over here, you'll get an idea of what I'm talking about with these sp hybrids. So the sp3 is long and skinny because it's more like a p orbital than it is an s orbital. If you did the percentages on how much of each, then you'd be saying 25% s and 75% p. So it's more like a p orbital than it is an s orbital. Now the sp2, that's about 33% s, 66% p, and then the sp is going to be 50-50, 50% s, 50% p. So you'll notice a difference in the shape as we go through these. If you look at the sp, you'll see it is a lot squatter, a lot shorter and fatter than the sp3 because it is a combination of one s and one p orbital. Now the thing is with, say, the sp2 is if we're only using 3 of these orbitals here, one s and 2 of these p's, then we're going to have one p left over that's not part of the hybrid. That's going to be important later. So we've got 3 sp2s and a leftover p. If the sp, with the sp, then we've got 2 sp hybrids and then 2 extra p orbitals there. So when you combine them together, you'll get, for the sp3s, this tetrahedral shape. For this one here, it's more like a trigonal planar, or really more like a trigonal bipyramidal shape. And then this over here is linear, or even octahedral if you want to look at all the orbitals and everything. So that's what those are the basic shapes of the sp3 hybrid, the sp2, and the sp. And everything is predicated on everything just being as far apart from each other as it possibly can be. So that's how it all works out. And those are the basic shapes. And you're going to have to know those specific shapes that I'm talking about here. So I'll run through and just show you how they're drawn. And it's really just the combinations of those shapes. So let's see. So sp3, as you can see, there's 4 sp3 hybrids. So this is how we work it out. Okay, so we look at the number of objects, 4 objects. It means we need 4 hybrid orbitals for those 4 objects, which means we need 4 orbitals to make those, which means we need 4 by sp3 hybrids. So what it looks like is going to be, to put those 4 sp3 hybrids, they're going to form this, whoops, that's awful. I'm going to do that again. It's going to form this tetrahedrally shaped doobie, like that. So you got all of them there, and that's not particularly well drawn, but yours doesn't have to be either, but it is tetrahedrally shaped. And I've tried to draw it so those lobes are as far apart from each other as possible, because we've got 4 of the lobes to put in there. And that's the way it works with VSEPR, if you remember, valence shell electron pair repulsion theory. I do have a little bit of stuff on that, a couple of fun quizzes that have extra credit. You should look at that and review it. You would have done it back in General Chemistry 1. Probably not this hybrid orbital stuff, but you might have done a little bit of it. You would have done it in my class if you had me for Chem 1. Does anybody have any questions about the sp3 hybrids so far? Okay, so you got the sp2s, that's going to be 3 objects. And it's not hard to count these objects. I'll show you, it's really easy, but I'll show you that in a bit. It means 3 hybrids. It means we need 3 orbitals. And then we've got 3 by sp2.
Will we only be drawing these for carbons?
No, you'll be drawing them for nitrogens and oxygens as well. And I'll show you how to do that. But your sp2 looks a lot like this. So these are all sp3s. Here you've got the 3 sp2s in the same plane, and then the p orbitals here. Now the p orbital is above and below, and we often express the p orbital as phased, which is why I've colored it in on top there. But the p orbital is above and below the plane there, and all of that's in the same plane, the sp2s. So that's trigonal planar there. All right, so that's the sp2, and then the sp. It looks like I'll have to erase that. The sp is going to look like this. The sp, we need 2 objects. Sorry. The sp, we need 2 objects that has to be made from 2 orbitals, or we need 2 hybrids. That's from 2 orbitals. So that's why it's going to be sp. And sp is going to be linear. So you have these 2 sp hybrids here, and then the 2 leftover p orbitals, which are 90 degrees to each other. And this one I'm pointing to here is coming in and out of the screen. So that's a p orbital, that's a p orbital. I can color that in as well. Just color in each lobe. But those are 2 separate p orbitals, above and below the plane there. There we go. All right, so if you remember what the s orbitals and p orbitals look like, I'll go back to that. You can see that when they're not hybridized, they just maintain their shape. So the p orbitals are just these 2 here that I'm talking about. The sp hybrid was the result of taking this s and this p and then hybridizing them to give the 2 sp hybrids. That's how it basically works. Does anybody have any questions about these hybrids here?
What is the name for the sp hybrid of that shape?
Well, it's linear. It's linear because this is where the bonds are going to form. Remember, we need 2 objects, and they'll be 180 degrees apart to be as far apart as possible. The overall shape, if you're just looking at the p orbitals and this, I mean, I would call that octahedral. But, you know, that's not really what it is. It looks octahedral, but it's really linear because that's where the bonds are. All right, do anybody have any other questions? Okay, so here is a summary of what we know about these hybrids. And this is pretty much for any atom that we can talk about that's carbon, nitrogen, or oxygen. So for sp3, we can have this is going to be single bonded. Everything's going to be single bonded. The central element can be carbon, nitrogen, or oxygen. The shape is always tetrahedral. The bond angle is 109.5 degrees. That's just something you're going to have to memorize because that's what it is for any tetrahedral shape, 109.5 degrees. The bond length here is going to be about 1.5 angstroms. An angstrom is 10 to the negative 10 meters. That's pretty small, but it's more for the sake of comparison, you can see this. If you look at sp2, we're usually talking about double bonded elements here. X can be C, N, or O. The shape is called trigonal, and the shape between the the angle between the sp2 hybrids is going to be 120 degrees. It's all in the same plane, so if you take a circle and you split it into 3 like that, then each of those is going to be 120 degrees. You'll notice that the bond length is smaller. 1.4 angstroms. That's because the sp2 is a bit shorter and fatter than the sp3. Now the sp, that one is going to be a triple bond. X can be C or N, the essential element can be C or N. It can't be O because O can't triple bond, it doesn't have enough bonds. That's going to be linear, 180 degrees, and this one is the shortest of all three, 1.3. Do you have to know these figures? No, not the bond lengths. You do have to know the relative lengths. You'll know that sp3 is longer than sp, but that it looks longer because it's, that's long and skinny, that's short and fat. All right, does anybody have any questions so far? Okay, let's look at an example. Actually, I won't do that. I'm going to go back. I'm going to go forward a little bit here, sorry. And we'll come back to the orbital diagrams in a second. All right, so let's look at how we might identify the hybridization of certain bonds. You can see how easy it is to do this. And really what it's about is counting the objects around an element in order to determine what its hybridization is. It's really easy because all you have to do is look at the kind of bond you see to that element. So sp3 is always going to be all single bonds. sp2 is double bonded, and sp is going to be triple bonded. So when you're looking at a compound, it's generally fairly easy to see what the hybridization of each element is going to be. Now, I want you to realize here, and this is important, it's the atom that's hybridized and not the bond. I'll say it again. It's the atom that's hybridized, not the bond. So what I mean is, these arrows here are pointing at these atoms that are at the end of these bonds. It's true that certain bonds lead to some hybridization, but what's important is it's the atom that's hybridized and not the bond. So you can see that this would be sp2 because it's double bonded. This one here is single bonded, so this one's sp3. This oxygen here is single bonded on each side. Now you'll notice there's a triple bond up here, so it looks as though the oxygen might be triple bonded, but it isn't. It's joined off to a carbon here that's joined off to another carbon. So that would be sp, where I've got the cursor, and that's sp at the end as well. And this oxygen here is sp3. Does anybody think they'd have trouble looking at a compound and determining the hybridization of each individual atom? Anybody have any questions about that?
What would it be for N since it has a double bond and then a single bond?
Well, you look at the highest bond order. Was that you, Sierra? Okay, I'm not sure who asked that. Okay, all right. Yeah, it's the nitrogen here. You look at the highest bond order, that's the double. So you go with sp2. So whatever the highest bond order is.
Okay, got you.
So for this one here, even though it's single bonded and triple bonded, it's going to be sp. So that's what you go with right there.
I have a question that's not totally related to hybridization, more to like the structure of the written molecule. I noticed the double bond is going in an alternating angle to single bonds, but the triple bonds are going in the same direction. Is there a reason for that, or is that just randomly how it was drawn?
Oh, no, it's not random. Not random at all. Let's go back to the table I showed you earlier. You can see that in the case of double bonds, the bond angle is specifically 120 degrees. So anytime you draw a double bond, it's always going to be angled like that. But look at the triple, linear, 180 degrees. So it's going to always be in a straight line.
That makes sense. Thank you.
All right. So that's how they're always going to be drawn as well. So, you can get some information by looking at the drawing as to what the bond angle is. But yeah, that's meant to be 180 degrees.
So then do the single bonds kind of move around then?
Move around? Not really. I wouldn't say they move around. I would just say that The bond angle depends upon what they're joined to.
And the repulsion between the electrons, right?
Yeah, because everything wants to be as far apart from everything else as it possibly can be. So that's why they sort of take on those shapes. All right, any other questions about this? All right, so this does relate to a test question. Let's take a look at the test question here that relates exactly to what we just talked about. Okay, so the question that relates to this on the test is this one, question 5. And there are lines here, I don't know, it's just not coming up. But you know, you're looking at these and you just trying to determine what the hybridization of each of these specific atoms is. And remember, it's the atom that's hybridized, not the bond. So does anybody want to tell me what they think for number 1, what the hybridization would be?
Sp3.
Sp3, because it's all single bonded. Remember that it's Sp3 single, Sp2 double, Sp triple. Now what about number 2? What hybridization is that one going to be?
SP2.
That's Sp2. What about number 3?
Sp3 again.
It is Sp3 because that's single and that's single. And number 4 is
SP.
Sp because it's triple. See, it's not hard. Now the shapes. Sp3 is tetrahedral,
Mm-hmm.
and the bond angle is 109.5. Sp2 is trigonal, and the bond angle is 120. And Sp is linear, and that's going to be 180. So that comes back to, let's go back here. Oops. That comes back to this table here that I was showing you earlier. So you will have to know this information, but my argument here is you already probably do. You already know most of this stuff about the shapes and the bond angles because you have seen it before. You just have to be able to link those shapes to those specific hybridizations. So yeah, you should know this table.
Could you repeat the number 4, please? The bond.
It's Sp, Victoria.
SP, because the highest number is triple, right?
Yeah, that's right. And it's linear and 180 degrees. And you can even see that in the diagrams, kind of like what Jonathan was asking about earlier. And you actually see almost 120 degree bond angle on the double bond here, the Sp2. All right, does anybody have any questions about that? Generally speaking, this is not something people do particularly poorly on, this particular question. It's not too bad. All right, any other questions about this? Okay, let's go back. What am I going to go back to? Yeah, okay, here. So we've got those questions where you actually have to determine the hybridization. And as a sub-question of this, well, sorry, it's really a sub-question of this kind of question here. So let's say you had to draw a molecular orbital diagram for something like CH2NH. So what you would be looking to do there is determine those hybridizations and then figure out how those hybrids were going to lock together and form bonds in a specific molecule. So now we're sort of ramping this up a bit. It becomes a little bit more complicated about what we're doing. All right, so let's see. I'm going to go through step by step and show you the procedure on how you manage to do that. Okay, I'm going to look to find, here it is. So I'll take it one step at a time here with the CH2NH. Now on the test, you're going to get 1 of 8 and you'll know what those 8 are, and I'm telling you it's going to be one of them. I have videos for all 8. I'll say it again, I have videos for all 8 that show exactly how to draw the diagrams and then how to put them together. All right, let's take a squiz. All right, so what we do first is we look at this, and you can see that it's double bonded. So we know that the C and the N are each going to be sp2 hybridized. Well, of course, whenever you draw any of these, the hybridization is always going to match. Right? You're never going to have an sp connected to an sp2 or something like that. They'll always be the same hybridization. So what we do is we draw the carbon and the nitrogen separately. So being an sp2, it's going to look like this. That'll be our P, and there's our sp2s in the same plane. So there's your P and the sp2s. Now, there's a couple of ways of expressing phase for P's. You can just color one of these in, or you can use plus and minus, if you want that notation. I prefer, I think, to go ahead and circle them in like that. Now, you might be asking, well, where do I get that diagram from? Well, you'll have to know the diagrams for each of those hybrids, and they're here in this table. So for the sp3, it's always going to be these 4 lobes, 109 degrees apart. sp2 is always going to look like the way I just drew it. And the sp orbital, sp hybrid is going to look like sp, sp, and then the p orbitals at 90 degrees to be sps. So that's just going to be the way that they are. Yeah, that's every time. It doesn't matter what the element is, they're always going to look that way. The hybrids are always going to look that way. All right, let's go back to what we were talking about here. So the N, I'll draw the same thing for N, and I'll join that together, sort of end to end. Okay. Yeah, it's probably optional to do anything with the P's really, as far as shading them in. I'm not really going to be that concerned if you don't shade or you do shade. But that's what we've got so far, is we've got 2 sp2 hybrids, a nitrogen and a carbon joined together. I know I haven't included what's going on with the hydrogens, but we'll get to that in a bit. Does anybody have any questions so far? All right, the next thing we want to do is put in the number of valence electrons. That's what's going to vary between these two. Now, carbon has 4 and nitrogen has 5. Now, we know this from back up here. Carbon has 4, nitrogen has 5, oxygen has 6. And you can get that by looking at the grouping, where they are in the periodic table. Now, when we're putting in the electrons, what we'll do is we'll do 1, 2, 3, and I'll put 1 in the P. I actually probably shouldn't have shaded it, but I'll put the electron here. That's probably why I don't shade them. So I know, because I can't draw the electron in the shade. But anyway, so that's where that and you'll notice they're all separated out. So you put 1 in each orbital. So I had 4 there because I have 4 valence electrons. Now I do the same thing with nitrogen. Now remember that 2 electrons are required for a bond, so I'll go ahead and put 1 in here. You'll notice I draw it the opposite spin of this one here. And that's because whenever we've got 2 electrons in the same orbital, they have to have opposite spins. So if you drew an up one, the one with it has to be down. And just for kicks, I'm going to draw these down as well. Now that's 4, but nitrogen needs 5. So I'm going to have to put another one in one of these. And that's what I did. I put the other one in this one over here. So you'll notice now that we have certain spaces where we can put other bonds. This one here already has 2 electrons in it. That is due to this lone pair here. See this lone pair? The non-bonding electron pair? That's these guys over here, the ones I just drew in here. And that only appears because nitrogen has 5 valence electrons. I had to put that extra valence electron somewhere else. Right here, actually. Anybody have any questions so far?
The only question I have is like, how do you know the C double bonds to an N?
Well, 'cause from the, well, oh, you mean when you're drawing this out?
Yeah.
Because when we draw this, we have to make it so the carbon has 4 bonds, but nitrogen has 3, and oxygen would have 2.
Gotcha. Thank you.
And that's the only way that you can do it to make that happen. But yeah, thanks for the question. That was good.
Is there any situation in which carbon will have unbonded electrons?
No. I don't think so. Hang on. I don't think so. Not in any of the ones you're given. But certainly nitrogen and oxygen will, or possibly may. Okay, what else have we got here? All right, so we draw in the templates. We put in the electrons, and then we want to bond them together. And then we want to put in the hydrogens. The hydrogens are all 1s orbitals, and those are going to attach to the ones that have 1 electron in them. And again, we put in the electrons so that they are opposite to the ones that are already in the orbital. All right, so that puts it, we put our hydrogens on, and then we can add the kinds of bonds that we're dealing with. Okay. I haven't talked about the sigma and pi bonds yet, but every bond in here, except for something between 2 separate p orbitals, is always going to be what we classify as being a sigma bond. And that's what I mean by sigma. This little O thing with a tail on it is a sigma bond. And the nature of that is just it's like a standard bond, really. But the pi bond, this one here, is special because it's between p orbitals. And you'll notice the pi bond is above and below the plane of the bond, just like the p orbitals are. All right, I'm going to show you a couple of videos of what that looks like. I didn't put in the 1s designations here on the hydrogens. I'll do that. But that completes the molecular orbital diagram for that compound. I'll just give you an idea about the distinction between pi and sigma bonds, and we'll go to a place. I don't know if it's going to work though. It was flash based, so I don't know if it works anymore. It might be a bit sad. We'll see.
Are pi bonds always with the p orbitals?
Always, and only p orbitals, pure p orbitals, not hybrids, right? Let's have a look. I'm going to try and go to the Orbitron and see if it works at all. It may not now, unfortunately. Okay. So let's look at, yeah, we'll look at nitrogen. I'll look at what this one here, sigma p. All right, let me see. I might try Firefox. Firefox might still work if I'm lucky. unfortunately, Flash is going to disappear completely by the end of 2020. It's going to be very sad, but that's how it's going to be. Oh, I'm going to live dangerously.
Dr. Musgrave, I have a question.
Yeah.
You said that we attached hydrogen to anything that has a 1. Why would we not attach it to a p orbital if it had a 1?
Let me go back here. Okay, could you repeat the question, please?
Yeah, so you said that we attach hydrogen to anything that has a 1.
Yeah.
Why would we not attach it to a p orbital?
Because the p orbitals are going to bond to each other, and that means that'll already have 2 electrons in it. So it would, even though we've got this seemingly empty space down here, the p orbital itself is actually both these lobes. That's why you would never attach anything else to them.
Thank you.
Okay. I'm going to live dangerously here.
I also have a question. So
Yeah.
for those Sp3s, you wouldn't have a pi bond, right? Because they don't have p orbitals.
That's correct. Yes, that's exactly right. Yes, there's no pure p orbitals with the Sp3 hybrid.
Perfect.
Okay, I wanted to show you just an animation of how 2 p orbitals could join together to form a sigma bond. And you can see it's just from like an end-to-end type situation. Now, contrast that with a pi orbital here. Take a look. See the difference? So the pi orbital appears between 2 pure p orbitals. And you can see, but it's characterized by being above and below the plane of the actual bond. I mean, the actual elements or the atoms are here, or the nuclei are here, where I've got the cursor here and here. So hopefully you can get an appreciation there of the difference between a sigma bond and a pi bond. But this is special. It only happens for p orbitals that are parallel like this, and not p orbitals that are joining, for example, end to end. Hopefully you can see the difference there. Does anybody have any questions? So generally, it's not difficult to be able to tell the difference between a pi bond and a sigma bond. But again, the pi bond can only appear, let's go back to where I was. The pi bond can only appear between 2 p orbitals here. And you'll notice everything else is a sigma. And you'll also notice there's no sigma designation on the non-bonding orbital because it doesn't bond. That's important as well. All right, yeah, go on.
You know how you said that nitrogen has 3 bonds?
Yes.
So does that mean there'll always be a lone pair with nitrogen if it's bonding?
If it's bonding 3 times, will there always be a lone pair? I'm just trying to think.
Well, I guess it depends who it bonds with then.
Well, you know what? I think in all of the examples, so I'm just going through my mind with them. They all do have a lone pair. Further, the oxygens always have 2 lone pairs, Julie.
Okay, so that makes sense.
Yeah. All right, I'm going to do 2 more examples, and these are examples also of ones that could be possible test questions for you. So I'm not just pulling something random here. Okay. So the one I'm going to do first will be the CH3OH. So when you look at that and you want to draw it out, and again, what we want to try and do is have 4 bonds on the carbon and 2 on the oxygen. Is anybody unclear about why I know this, why it's 4 bonds for carbon and 2 for oxygen. Is everybody okay with that? Okay.
I'm okay with it, but if you have additional information on it, I'd be open to hearing it.
There isn't really any, Julie, except what I had said earlier about how many electrons they need in order to get their octet. So oxygen being in group 6 needs 2, and nitrogen being in group 5 needs 3. Carbon needs 4. That's really it. Is that okay? All right.
Are we allowed to have the periodic table on the test?
I give you, it's part of a test. It's attached to it. When you print it out, you'll see it.
Okay, thank you.
Okay, so when I draw this, I'm going to draw it in such a way that that happens. So it's going to be 3 hydrogens. I'm drawing too close to the top here. Put it down here. And then OH. And that's what it's going to look like. And that's how, it's the only way I can draw it so that the carbon has 4 and the oxygen has 2. So I know that they're all single bonded. That means that that's going to be Sp3 hybridized, and that's going to be Sp3 hybridized. I'll stop there for a second. Is anybody concerned about anything I've done so far? Okay, so let's put this together. We've got our C and we've got our O. Now the C is going to be Sp3, which means it's going to be this one here with the funky lobes on it, 4 of them. Remember, I've got videos for these as well. And the oxygen's going to be the same story. And they're all going to be Sp3s as well. And carbon has 4 bonds. Sorry, 4 electrons, 4 valence electrons. So I've put 1 in each. And then the oxygen has 6. So there are 1, 2, 3, and then 4. And then I have 2 more that I've got to put in, and those will go in 2 separate orbitals, 1 and 2. Now that becomes 2 non-bonding pairs. I don't have to show them on the original diagram, but I could if I wanted to. But there they are in the actual orbital diagram. Does anybody have any questions so far? All right. So the hydrogens. Hydrogens. They're the 1s, and we've got 3 of them. Opposite, I draw those electrons opposite what I did earlier. And then we've got our bond types. Now, you'll notice there's no pure p orbitals in an sp3 hybrid on either side. So there are no pi bonds. It's just going to be straight sigmas all the way around. So sigma, 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 and sigma. You'll notice there's as many sigma bonds as there are bonds. 1, 2, 3, 4, 5.
Can I ask a question?
Yeah.
I noticed that you put in the 6, 1, 2, 3, 4, 5, 6 electrons over in the
Oxygen.
oxygen, but in the carbon, okay, because there's no nitrogen. All right, never mind. I withdraw my question.
Okay, Julie. You understand that that's the number of valence electrons we pull off the periodic table. That's how
I do. I was just thinking the other one had 5. I had to go back and look down again because they've been next to each other since you've had like 4 and 5. So I get it. Thank you.
All right. Any other questions about these diagrams? You know, they're not that bad. They look really bad initially. You know, you look at it and say, oh gosh, how am I ever going to do that? And you know, It's just like my psychiatrist told me. I told him I was afraid of stairs. He told me just take it one step at a time. I think it's good advice. I think it's good advice.
On the oxygen, where are the 6 electrons? I see 5.
1, 2, 3, 4, 5, 6. See, there's 2 in each of these. Rebecca?
I can't see where you're pointing.
Oh, sorry. Here. I'll circle it. 1.
Okay, 1.
And then there. That's still got 2 electrons in it as well.
Oh my gosh. Okay, I thought that was a P. Thank you.
Okay.
I got it. On the top one, I thought that little one sticking off of the, okay, that I'm with it now. Thank you.
Good? You good?
Yes,
All right.
yes,
Okay.
yes.
All right. Any other questions? All right, I'll do one more example. One more example. Okay, let's do, I'll do a triple bond one here. Spoiler alert. Okay, so that'd be, I guess, a C2H2 is what it is. Now, if you're putting this together and you want everything to have 4 bonds on it, it has to look like this. That's the only way. It's the only way you can arrange that so you get the 4 bonds on the carbon atom. So it has to be triple bonded. Everybody okay with that? Anybody have any questions? Okay. SP, SP. That's because they're triple bonded. All right, any questions so far?
What's the reason that the 2 H's can't be on 1 C?
Because there's no, then you're going to be short bonds, right? There's no, where else are you going to put your other bonds, Julie?
But how do you know automatically that it's triple bonded?
Because both carbons have to have 4 bonds, right?
Oh, and the other one wouldn't have it. Okay.
Yeah, it's just impossible. There's just no other way of doing it. I challenge you, Julie.
Okay.
Come up with another way.
That's okay.
No? All right. All right. Not going to accept the challenge? Okay. All right, let's take a look at the SP hybrid set. So that's going to be the C. And we've got our SPs, 1 on each end like that. And then this one's a bit of a bear to draw. Oh, that's awful. It's a little bit better. So that's a P and that's a P. So that's how it's going to look on both of these puppies. All right, does anybody have any questions? All right, so carbon, we got 4 valence electrons, so I'll put 1 in each orbital. Remember the p orbital, that whole thing is a p orbital going top and bottom. And I do the same thing on the other side, but I make the electrons kind of down on each. There we go. So 4 in each of those. Anybody have any questions? All right, let's put in the hydrogens. And those will go on the ends here. So H and H. And then 1s and 1s. Remember 1s because it's here, 1s. It's in the top one here, 1s. Any questions so far? We're not quite done yet.
The location of those arrows, you started with the on the carbon, so you started left, top, top, right. Does it matter if it's going to be left, bottom, bottom, right?
Nah.
I don't know if I explained it right.
No, you're right. It won't matter.
Uh-huh.
Victoria,
Okay.
you're good. You're good. But make sure that for any bond where you've got two electrons joined together,
Mhm.
or any non-bonding situation, make sure they're always opposite direction. You know, one up, one down. Okay. But it doesn't matter which one's up, which one's down, as long as they're opposite.
Will you require us to write the 1s by the hydrogen?
Yes, because it is part of the molecular orbital setup, just like the SPs are and the Ps are. Any other questions? All right, let's put in those orbital types. This one's sigma, this one's sigma, and this one in the middle here is sigma. Between the two SPs, they're all sigma bonds. And then we've got going to have two pi bonds. We're going to have one here at the back, and then one here on the bottom. So you've got to be very clear about where you're joining those together, understanding that the pi bond in both instances covers top and bottom of those p orbitals. It's a bit of a challenge to draw, I will admit, but that's how they are. That's how they're drawn.
You don't have to label the pi bonds at the bottom because it's the same.
It's the same bond. In fact, if you do label the pi bonds at the bottom, I'm going to begin to wonder if you understand what a pi bond is.
Mm-hmm.
You don't want me wondering that.
So we just draw the lines connecting it just to show that.
That's right, because you're trying to show which p orbital is connected to which p orbital. And the ones that are sort of, in the plane, the ones going up and down, the vertical ones, those are going to join together. And then the ones coming in and out of the plane, those are joining together as well.
Okay, gotcha. So, will hydrogen always have a 1s?
It will, because of where it is in the periodic table.
Gotcha.
Right?
Mm-hmm. Thank you.
Dr. Musgrave,
Yeah.
could you cover the sigma one more time, just in a nutshell?
The sigma is everything that isn't a pi. And the pi only ever appears between p orbitals that are parallel to each other.
Okay. But
that's what I wanted to go with. Go on.
I'm sorry, is sigma connected to the hydrogen location at all, or where we're putting those sigmas? I guess that's what I'm trying to ask.
On the bonds themselves. They're the bond types themselves, how they're bonding together. So it's the sp1s bond. What kind of bond is it? Well, it's a sigma bond. The sp-sp bond, that's a sigma bond. So, it's going on the bond.
Gotcha. Thank you.
All right. Any other questions?
Where the p orbitals are connected, it should be the two that are up and down are connected, and then the two that are angled.
Yes.
So there's a little bit of like a cross, right?
Yeah, unfortunately, yes, because it's kind of three-dimensional. Yes, that's right.
Okay, so it's hard to see on your drawing.
Yes, it is.
But that is how it should be, that the matching orbital angles should be bonded.
Exactly. Okay. Yes, exactly right. Because
Okay.
that's the nature of the pi bond. They can only bond if they're parallel to each other.
Okay.
You
When I'm
can't.
drawing it, it looks like there's more of like a cross.
Yeah, I know. It's hard.
Where yours look more parallel the way you've drawn them.
Okay, but I am going to bring something else up here, Rebecca.
Okay.
I suspect this might be a good time to do it. All right. Okay. So let me put it to you this way. I'll show you what I don't like. Maybe that would be helpful. I do get occasionally, so here's the P's. I do get occasionally people who do something like this. So this one's fine. For the one that's going to join with that, that's all hunky-dory. But then I get this. I don't like it.
The drawing is so much prettier though.
You think? I disagree.
I'm just kidding.
I disagree. I think it looks bloody ugly.
Okay, so they need to, the angles need to match, which of course that's from the diagrams, but then when you do it, if you twist the second one to the correct angle, there is going to be a, like, in order to not go through the orbital, I had to cross the.
Yes, it's an unfortunate thing, but it's true.
Okay.
And I'll just do that. Whoops. Go back here again.
But like you said, just because it's bloody ugly doesn't mean it's bloody wrong too.
Oh, well, I want them to be pretty. Let me show you.
When I did mine, I had to like make arches instead of just drawing connection lines. It was kind of like a rainbow.
Yeah.
Yes.
Okay, so here's what I'm doing. Right?
Uh-huh.
Okay, pi. And then this is what you were talking about, Rebecca. See?
Oh, so you did go through the orbital.
Well, behind it.
Okay.
Can we go over it?
Yeah.
Can you go over it? Well, then your pies are going to cross.
They do. Yes, that's what I'm trying to ask about.
Oh no. Well, I think that's. I like this. Yeah. Well, I mean, I can deal with it.
See how it's crossed?
I can deal with it. I mean, you can, as long as things are joined together right, I'm okay with it. But yeah, it could happen.
But you'd rather it go behind.
Well, that's prettier. Now, is it wrong to do it? No. But this is, if you're going to draw them parallel, make them look parallel. That's what I say.
I understand. Okay.
And we use pretty colors.
That's up to you. The pretty colors business depends on how much time you've got.
Or how many pencils.
Yeah, it ain't going to score you any extra points, I can tell you that. Pretty colors. All right, any other questions about these thingies? All right, let me show you something else here. Oops, no, wrong.
I do have a question on a previous problem we went over. The CH2NH, it only has one pi bond, correct?
Yeah, that's right, because it was double bonded. Yeah, that's right.
Okay.
Let me see. I'll pull that back up.
I was just wondering because I marked it on like the bottom one too, but then I realized that.
No, that's right. Here we go.
Long thingy.
Yeah, there you go. Do you see that? You got the 2p orbitals here, so we just got the one pi bond. The pi is up here, but we don't label the bottom.
Got it. Thank you.
Okay. All right. Let me show you the possibilities. And they're actually on the bottom of the first page of the the blue book here, or this problems test 1. And question 4 will be the orbital diagram showing all hybrid orbital types, pi and sig, and bond types, pi and sigma. It'll be one of CH4, CH3NH2, CH3OH, HCN, C2H2, C2H4, CH2O, or CH2NH. I have videos showing how to do all 8, but it will be one of those. So you should probably practice all of them. All right, does anybody have any questions? Any questions? All right, there we go. Let's go back now to question 1 while we're here. I won't do this one though. I'll do the one I've already got. This one. Okay. So question 1, you can see the kinds of questions you're going to be asked here. Hang on, I need to make this a little bit smaller. Hang on, it's not being very. It's not being very cooperative here. I'm just trying to get this to be a little bit smaller. No, I'll just do this. All right. So there's 4 parts to it, A, B, C, D. The first one is a question about dipole. The second one is going to be about boiling point. The third one is going to be about solubility. And the fourth one is going to be some sort of orbital question like we've been talking about. So for this one here, for example, if you were looking for the weaker, lowest, or least, because it could be highest, greatest, or most as well, so you've got to be careful of that. But this is weakest, lowest, or least. You've got your LIO and CO. What you do is you look at how far apart they are on the periodic table. And we've got LIO and CO. And you can see that the Li and the O are very far apart, which suggests that there's a great difference in electronegativity, whereas C and O are closer together, which indicates that there's less electronegativity difference. So that would be what you would do here. You'd put as reasoning lesser change in electronegativity or lesser difference in electronegativity. Smaller distance on the periodic table doesn't cut it for me because, yeah, I mean, that's what you're looking at, but that's not the real reason why the dipole on this one is going to be smaller than the dipole on this one. It's got to do with a smaller difference in electronegativity.
So the greater the difference of electronegativity, the greater the dipole?
Say it again, please.
So the greater the distance, aka greater electronegativity, will be a greater dipole?
Yeah, greater difference in electronegativity though.
Greater difference, okay.
Yeah.
And it's asking for the least, so it would be the CO, okay.
Yeah, that's right. That's exactly it. But you know, the reasoning here, if you just put lesser difference in electronegativity, I'm happy as Larry. That's okay. So boiling point. What you've got to do is look at the two things and determine what the intermolecular force is with each of these. So the little cheat thing that we talked about earlier, let me bring this back up over here. We know that, oops, I did it again, didn't I? Okay. So we know that all CH is going to be van der Waals. We know that CX is going to be dipole-dipole. And we know NH, OH, FH is going to be hydrogen bonding. So you're looking at these two and you can see they're both hydrogen bonding. So that doesn't give you a great deal of help. But the difference between these is that one is branched and the other one isn't. So what I would say is the one that is branched would be the lower boiling point. That would be the one you'd circle. And you can say both as reasoning, both H bond, but this one's branched.
Are they both branched, but the second one has more branching?
Well, actually, I don't see any branching at all on the first one. Remember when I talk about branching, it's to do with things coming off the carbon chain or carbons coming off the carbon chain.
But the first bond that's at 90 degrees, is that significant or not?
Not really, but because, you know, they're all joined together in a straight line.
Okay.
But with this one here, clearly there's carbons coming off it to make it branched. Yeah. Think of it like a tree limb. You know, whether it's straight or whether other branches come off it. For something like this one, it could be solubility in water or solubility in some kind of hydrocarbon. And we've got the hydrocarbon here, C7H16. What you want to do is, for that one, actually I'll So for C7H16, we know that that's going to be van der Waals. And then we look at the other two. And that one is going to be hydrogen bonding. And the other one here is going to be dipole-dipole. And what we're looking for is a lesser solubility. So the one that's least compatible with van der Waals here is going to be this one. And that's how you'd work it out. And that would be, doing that would be sufficient answer. Just putting in the intermolecular forces like that, I'd be happy with that. But make sure you also put an intermolecular force on the solvent as well. Does anybody have any questions about C? Okay. And the last one here is going to be about bond angle or bond length. It could be either one of those. So we'll look at bond angle for this one. So you'd probably have to draw these out just to get an idea of the hybridizations. But HCN looks like this. And CH2 and H looks like this. And then you can see the hybridizations. That's going to be SP. And that's going to be, let's see, we're interested in HCN bonds, so that's going to be SP2. They're both SP, the C and the N in the first one, and they're both SP2, C and N in the second one. But what we know is that SP is going to have a 180-degree bond angle, and SP2 is going to have 120. So the one that has the lesser bond angle would be this one. Now, let's say it was asking about bond length, then it would be the opposite. SP would be shorter, and the SP2 would be longer. So you've got to be very careful to make sure you read that question properly. It's either going to be about angle or length, one of the two. And you've got to make sure you're answering the correct one. Does anybody have any questions? Did I lose you? And did I lose you? I just want to make sure everybody's okay.
No.
No, okay, good.
I can hear you.
Okay, good, good. Does anybody have anything else they want to ask about here? All right, well, you got plenty to practice now, so I recommend you do that and you don't leave this sort of till the last minute, because this is stuff you can look at now, stuff you can study, stuff you already know is going to be on the test, so you should be able to go from there. All right, we'll leave it there for today. I'm hoping that we won't have any Zoom issues on Wednesday. I think everything will be back to normal. And I will see you all at 12:30 on Wednesday.
All right,
Quick
thank
question,
you.
Professor Musgrave. I haven't looked too in depth at this, but do you have the answers to the test files on my courses for the old tests?
Yes, they're
Okay,
in the
okay.
same folder. They're under a subfolder called keys.
Yeah, I haven't even checked. Thank you.
Okay. Anybody else have any other questions? I'll hang around. I like to be the last one to leave.
Some questions regarding the lab.
Yeah, can you wait a bit? Let me make sure that nobody's got any other class-related stuff, and then I will answer any lab-related questions you might have.
I'm gonna wait for the lab as well.
Sorry, what's that?
I'm gonna be there for the lab as well.
Okay, Francisco, no worries. All right. Oh, let me see how many are left here. Oh. $17 still. Anybody else have any class-related questions? I will answer lab-related questions once all the class-related questions are over with here. Anybody else? Okay, it doesn't look like anybody has any class-related questions. So Sierra, what's your question?
Okay, so part 5, number 6, it's asking you to draw the structure of diethyl ether. So I tried to do it on my own, and then I went and watched the video after just to see how I was doing with it. And in the video, you had CH3 bonded to an oxygen, and then on the other side bonded to another CH3.
It was dimethyl ether, right? Not diethyl ether in the question you're talking about?
It says diethyl ether.
No, I don't think it does. Not in, well, actually, maybe I've got the wrong part. Let me think.
Because when I did it, I
is
had a CH2 bond in between the CH3 and the oxygen on both ends.
Well, I mean, to be super clear here, I'm just going to show you the way it should be. If it is truly diethyl ether that you're talking about, and I suspect it isn't, actually, Sierra.
Because I'm looking at number 6, and it says the structure of diethyl ether is, and then it asks for the drawing.
Okay, that's diethyl ether. And this one here is dimethyl ether. But I might be thinking about the wrong part. The last question, I know definitely, the question in the last part, at the very end, the application part.
Yeah.
I know that that's dimethyl ether. And then there's another question about diethyl ether, but that's diethyl ether there as a line structure. So it is CH3 connected to CH2. The reason we know that, that's ethyl.
Okay.
And there's 2 of them. So it's diethyl. The oxygen part they're joined to is the ether part.
I got you. Okay.
Right.
Yeah,
So
because I have the CH3 bonded to the CH2, which is then bonded to the oxygen.
But it's on both sides.
Maybe it's, I don't know. Did you ask something about diethyl? I'm like, maybe it's a typo. I don't know.
No, it's not a typo. I asked about it in one of the parts. I just can't remember exactly where. And then there was another one. This was methyl ethyl, which has methyl on one side and ethyl on the other.
Oh, so dimethyl ether is an O bonded to a CH3 on each end?
That's right.
Oh, I gotcha. Because then I was trying to make the isomer, and I was like, I don't even know. I'm going to have to look up some compound because I don't even know what to do for that.
Now, the isomer, I'm not going to give you too many hints about that, but look at the ordering. You've got COC. Think of another way you could order it and see if you can come up with an isomer that way, okay?
Gotcha.
Okay.
Thank you. And then also for part 7 on that, it says construction of an unknown. What was the unknown you wanted us to use?
Don't worry about it. There won't be one.
Okay, gotcha.
I guess it was unknown, Sierra.
Oh.
I'm just kidding. I'm being silly.
I know.
All right.
Thank you.
Okay. Is there anything else, Sierra?
I think I'm good. So dimethyl is the CH3 bonded to the oxygen, and then the diethyl has the CH2 in between. I got you.
All right. Okay, Francisco.
I think you kind of, with answering Sierra's questions, you kind of answered mine. I wasn't too, doing the line structures, I just didn't feel like I was giving enough information. So when I was answering the question, so I was trying to label everything, but you just want just the line structure.
Actually, for the one you've got there that I'm looking at, it looked like this is a line structure. You don't draw in the hydrogens at all.
Okay.
You with me?
Yes.
Now that has some interesting implications. If you've got CH4, how would you draw that as a line structure? If you're not supposed to draw in any hydrogens.
Is it just a dot?
It's just a dot. That's exactly right.
Okay.
Whereas something like C2H6 would just be a line, just a straight line, between 2 dots, basically.
Yeah, but exactly. So I have it just how I.
Yeah. Perfect. Lovely.
But I just feel like that. Well, I guess this is what you're trying to teach us, which it just doesn't say much.
I know, but you're not saying much. It says so much.
Okay. one of my buddies graduated. He works with me night shift, Stefan, and he's trying to look for a job as a chemist. And I had to ask him for a little bit of advice. And he's like, just what you're doing is enough. You're adding too much information, and that's not what your teacher probably wants. So I just want to double check with you.
Stefan was right.
Yeah, he usually is.
All right. Anything else, Francisco?
No, thank you.
Okay. Keisha, you're still here. Do you have a question? Keisha? No question.
Sorry, no, you answered the question that I had. It was regarding that on the last part, the application part C. I emailed you about that one, but you repeated the same thing. I still don't get it.
What did I say exactly?
You said try to reorganize the C dash.
Oh yeah. So it's the COC into something else. I'm still not going to give you any hints about that.
I've been thinking about it for days, and I'm still lost. Okay.
Well, you could always Google it.
I will.
But I don't know. I don't know. I can't really say anything else because it'll just give it away.
So, Professor, oh my gosh, I think I just did the whole lab wrong. So, like, when you say you want it line structure, you want it like how you just wrote it up there on the example?
Yeah.
Oh my God.
No,
I just did the whole lab wrong. Oh my God.
No, it's okay. You can leave the structures the way you have them. Just put the line structures next to them.
Okay.
It'll be fine. It'll be fine. A lot of people have done that. I mean, they've already put it in. Then I grade them. I give them like 80 out of 100 if they've done everything right, except they haven't put it in line structure form. Then I tell them to resubmit in line structures.
Okay. Well, at least I'll have both for reference.
It's all right. I mean, it's okay to have the other ones there. It makes it easier to draw the line structure. It shouldn't take you long, Sierra. I think if you understand line structures, it should only take you about 10 minutes to do that.
Yeah.
I'm
for
serious.
Sure. Thank you.
I'm serious.
I'll time it and I'll let you know next class meeting.
All right. You got a deal. You got a deal. All right. Anybody else have any questions for me? Anybody else who's left here have any questions for me?
Oh, I have another question. I'm sorry.
Yeah, that's all right.
When you're asking for the functional groups, is it okay if we put the R's in there for where it would fall into something else? Okay.
Absolutely. Yeah, that's fine.
Okay, perfect.
Or not. I don't care. Either way. All right. Any other questions?
Musgrave, for the last page where it says 6 an application and 7 construction of unknown, so we still do the application, just not the unknown?
Right, because I didn't give you one.
Perfect.
Okay. Any other questions?
This is to be turned in by 4:40 on Wednesday, right?
That's correct.
But technically, we can still do it at 2 p.m. while we zoom in.
Yeah, that's right. I'll be here.
Okay.
You know, I'll be here, and I'll be here to answer your questions. You know.
Another one actually for C of the benzene and its derivatives, the 2,4,6 trinitrotoluene. I don't know.
Toluene.
Toluene. Like extra stuff. It says the nitro group NO2 is actually that, not that.
Yeah, it doesn't. You can just draw it as. You can just write it in as NO2 on your structure, Courtney.
Okay.
All right. Any other questions from anybody?
Did you count attendance today, Dr. Musgrave?
Well, I don't call it. I get it off Zoom.
Okay, cool.
Yeah, I'm kind of clever like that. I can get it off Zoom.
Well, the problem is that they updated the whole Zoom resolved I have a notification at 1 p.m. So the website updates, it says it still had a problem. That's why.
Oh, okay. Well,
yeah, I couldn't log in.
Oh, yeah.
Don't log in.
Right, fair enough. There might have been people who weren't here today because of that. I'll take that into account.
Because my previous class, the physics, it was not working.
No, that's right.
With the same notification.
We kind of got lucky. It's I think it. Yeah.
All right, cool. Thank you so much.
All right. Any other
All right,
questions? Yeah. Any other questions? Any other questions? Brianna, Brittany, Amber.
No, my questions got answered from everyone else. Mine was really just what Francisco asked, so I'm good.
All right. Okay, good. Brittany,
Yeah,
Amber.
no, I just stuck around.
I'm just kind of hanging around.
Okay, just curious. Just curious. Okay, fair enough.
All right. Thank you. Bye.
All right. See you guys later then. Bye.
Thank you. Bye.